Hey everybody, I am back and we are talking about NMR again. In this video I want to go over the third major factor that we look at in interpreting NMR spectra, and that is going to be intensity, also more commonly known as integrations. Alright, so when we say integration, here's what we're talking about. If you look at any NMR spectrum and you see the peaks that are for a signal, you'll see that they're typically, curves, right? If you look between them, even the ones that are very, very flat looking, they have open space in the curve. And if you've ever had a calculus class, you probably know that, you can calculate the area underneath a curve by doing integrations, right? And tongue-tied, antiderivatives. And so this is what we're analyzing here, is we're actually looking to approximate the area underneath these curves, and that's going to give you information about ratios of hydrogens causing each signal. Now you can breathe a sigh of relief here because you don't actually have to calculate area underneath the curve. The machine does that for you. The NMR spectrometer and the software does it for you. What we have to do is we have to be able to interpret. All right, and like I said, we're going to be using this to determine ratios. So just to give you, an example here, let's say we have CH3, CH2, Br. All right, I think we can safely say here that in this problem, we've got two different types of hydrogens. So we're going to have two signals, signal A and signal B, right? If you look at the number of protons that are in group A here that are causing signal A, you'll see there's 3 of them. If you look at the number of protons in group B, it's 2 of them, right? So our ratio of A to B is going to be 3 to 2. All right? If we look at another one, come on, there we go. If we looked at one like this, a little bit more complex looking. That's wrong. Okay, that did not turn out well. I got a little bump there. There we go. Okay, so if we look at this one, we see this is actually a symmetrical molecule. So if we're looking to group protons, we can say that, well, we have 2 identical methyl groups here, and the methyl groups that are over on this side are also identical, right? So all the protons in these methyl groups are going to be A. We have an individual proton there and an individual one there that are identical to each other. And then we have these groups right here that are identical to each other, right? So we have A to B to C, all right? And if we go through and count these up, right, all the H's that we have in group A, there's 4 methyl groups, so that means we're going to have 12 of them. We have 1 proton for each of the B circles, so that's going to be 2 protons giving signal B, and we're going to have 4 to signal C. It's a 12 to 2 to 4 ratio. If we reduce that down to the lowest numbers, it's actually a 6 to 1 to 2 ratio, right? And so if we don't know what the structure is, but we can somehow figure out this ratio, then that gives us a big, big heads up on being able to figure out this structure. My personal opinion, I think integrations is going to be the most useful point that we get from an NMR spectrum, and is the most helpful hint to getting the overall structure. All right, so that's why we look at integrations. Now let me give you a couple of examples of how to analyze. And it's actually pretty simple to do. You are going to have different situations, all right? And depends on what the spectrometer and the software give you. Not every NMR setup is created equal. Sometimes they give you a lot of information, All right. Frequently, you'll see a situation. Whoops. I want to use SIT for situation. Situation 1. You have a situation where they will give you in the spectrum something called integration units, and I'm just going to abbreviate that as IU, so I don't have to write that all out again. All right, and that should be KNOW. And it's also a situation where you happen to know the molecular formula, right? Maybe you're working a problem, the formula's been given to you, right? But you don't know what the exact structure is. So you take the spectrum, you know the formula, and you get a spectrum with integration units, right? Let me show you what I mean by integration units. Sorry for the poor quality of this. Whoops. I just literally took a snapshot of my laptop. But here you can see a spectrum, and you'll frequently see a couple of things pop up on a spectrum if you do integration analysis. Number one, you'll see that next to the signal themselves, you'll see this long sort of S-curve line that's next to it. In fact, it actually looks a lot like an antiderivative symbol from calculus, right? These are your integration marks or integration curves there. And next to it on the other side, you see a number that the machine has spit out. Like for signal A in this photo, it says 54. For signal B, it says 23. And for signal C, it says 33. And you'll notice that the integration marks are proportional to these, right? For the one that says 54, the S-curve is bigger than the one you see for 23, for example. The 54, 23, and 33, these are your integration units. All right, so what I'm going to do is I'm going to show you how to figure out the ratio of a spectrum of protons in a sample given this situation. All right, here's what you do. All right, first, you're going to total the number of integration units. All right. So in the last one, we saw, in the one I just showed you, signal A had 54, signal B had 23, and signal C had 33. So that gives you a grand total of 110 integration units. All right. Next step, you divide total number of integration units by the total number of protons. All right. And that particular compound had a molecular formula that was given to you as C9H10O2. All right, so we just simply take our total number of integration units, 110, divide it by 10, and we end up with a total of 11. This is going to be 11 integration units per proton. Okay. All right, I'm running out of room, so I'm going to erase at least part of this. I'll keep that part up just for reference. And then C, in step C, what you do is you take the number of integration units in each signal and divide it by the integration units per proton. So for signal A, we had 54 individual units. We're dividing it by 11 units per proton, and that equals 4.9. For B, we had 23 units. We're dividing it by 11. That gives us 2.1. For signal C, we had 33 divided by 11 gives us 3. Okay, so we end up with a we end up with a ratio of 4.9 to 2.1 to 3. All right, now this is close enough where we can round. 4.9 rounded up is approximately 5. Right, we're not going to have, obviously, we're not going to have a fraction of a number of protons. We're going to end up with whole numbers. All right, so this is going to be a 5 to 2 to 3 ratio. So this would indicate that signal A is being caused by 5 protons, signal B is being caused by 2, signal C is being caused by 3. Okay? So it's a very straightforward process if you have the number of integration units and the formula. It's not always quite that easy, though. Let's look at situation 2. Situation 2 is where you have integration units, but no formula. Wow, that's really ugly writing. I apologize. I really do look like I'm in kindergarten. All right. So let's look at this previous one. Let's look at the previous one that I just did, except let's pretend that we did not know the formula. All right? There is a way to do this. It's a little bit rougher, but it still usually works. All right? So we don't know the formula. We do know that A to B to C has a ratio of 54 to 23 to 33 via integration units. All right. So what we do in this case is we're just simply going to take every number here, every signal, and we're going to divide it by the lowest number of integration units that we have given. So in this case, we're going to divide all of these by 23. And when we do that, that gives us a ratio of 2.35 to 1 to 1.43. Now that's a pretty ugly ratio, right? We have two decimals that are pretty far away from being whole numbers, especially the 0.43. But what you can do here is, when you have numbers like this, you can multiply them by whole numbers to try to get them closer to the individual measurements being whole numbers themselves. For example, in this one, I could take the whole thing and multiply it by 2. All right, and that gives us a ratio of 4.7 to 2 to 2.86. And if you round the two extreme numbers on the very ends, this does, again, look pretty close to 5 to 2 to 3. All right, so this method turns out a little bit rougher sometimes, but usually it will get you where you need to go, in case you don't happen to know your molecular formula. And realistically, if you're working in a lab somewhere, you might not know this. Maybe you just synthesize something and you're trying to discover what the structure is, right? So this is a good way to do it if you have integration units but no formula. All right, the third situation, which is more and more uncommon now that technology and software is more advanced, there are certain situations you might run into where you only have integration curves or integration lines, but not integration units. I hate to date myself here, but back in my day, this was the norm. We usually didn't have software that could generate integration units. Now we do. Our spectrometer generates integration units. So like I said, you probably won't run into this one as much, but it is certainly possible. So let me show you how you would go about this. All right, and so what I'm going to do here is I'm going to show you a couple of examples. This is, by the way, this is a website called Web Spectra, and you can see the address right there. It's hosted by UCLA. It's fantastic. It gives you really good practice on doing different types of spectral analysis. It does all sorts of stuff that we will not get into, like, you know, where it says DEPT and cozy spectra and stuff. We're not going to get into that, but they do have NMR spectra and IR spectra on here as well. So let's take a look at this one, and you'll see what I mean. This one is C4H802, and it's a little hard to see, so I'm going to enlarge it. If I enlarge the NMR spectrum here, you can see that we have integration markings or integration curves, right? They're going to be those red curves, red S curves that you see there, but we do not have any integration units. All right, so what you have to do here is you have to estimate, you have to sort of approximate the ratios of the lengths of these lines to each other, right? Back in my day, we would literally have printouts of these, and we would use rulers. We would use rulers to measure them, either in centimeters or inches, doesn't matter. You just have to keep it same for all of them, and we would use those as a starting point. All right, so if you happen to have a ruler or something, feel free to break it out now, pause the video, and kind of measure the lines. I'm just going to eyeball it here. For this one, I'm going to just make the signals left to right, A, B, C. All right, and I can see for signal A, obviously, it's going to be the one that has the smallest S curve. So I'm just going to make that one a baseline of 1. I'm going to say A equals 1. All right. If I move to signal B, the one in the middle, it looks to me to be about 1.5 times the size of signal A, the S curve for signal A. All right, so I'm going to make that 1.5. Signal C is about the same size as signal B, so I'm going to make that one 1.5 as well. Again, you can get more exact measurements if you use a ruler. All right, so that gives me an initial ratio of 1 to 1.5 to 1.5. All right, again, we have fractions here, so I'm going to multiply everything by 2, and that's going to give me a ratio of 2 to 3 to 3. So I think for this one, I would have 2 to 3 to 3. All right, I can confirm that by looking at the answer here. 2 plus 3 plus 3 equals 8, and we do have 8 protons in our formula, so that's a promising start. And if I look at the answer here, the answer is ethyl acetate, you'll see we have CH3, CO, CH2, CH3. So we do have one carbon with 2 H's and 2 other carbons with 3. So this would actually agree with my analysis, right? So you can see it is very, very possible to make these approximations even if you don't have the integration units. Let me go back. I don't know how many times I'm going to have to hit the back button here. There we go. Let's take a look at another one. All right, this is C4H7O2Br. All right, and sometimes they can be a little bit tricky to look at. And this one, you see 2 of these have actually kind of bled together, right? So you see that from about chemical shift 3.9 to 3.5 or 6 or so, you see what looks to be a singular S curve, but it has sort of a bump in the middle of it. That's actually 2 individual signals that are very, very close to each other, right? And they're just sort of overlapping. So what you have to do is you have to be able to sort of try to accurately, estimate where one ends and one begins. If I'm looking at this closely and I sort of estimate here where one ends and the other begins, it looks to me that those are 2 S curves that are about the same, about the same size. So I'm going to say, again, going from left to right, A to B to C, I think the first 2 are about the same. So I am going to say those are about the same. And then the third one is, I would say, a little smaller than each one of those. I would say the signals, or the S curves for the first 2 are probably about 1.5 times as big. So, actually, no, I'm going to take that back. I think actually the first signal looks a little bit bigger. Now they look a little bit closer at it. So I think the first signal is about 1.5 times as big as each of the other 2. So here's what I'm thinking for this one. One on the left, signal A, I think we assign a value of 1.5. Signal B and signal C look to be about the same size, so I want to assign each of them a value of 1. So we have a 1.5 to 1 to 1 ratio. Again, if we multiply everything by 2, that gives you a 3 to 2 to 2 ratio. All right, so I think in this case, signal A is being caused by 3 H's, signal 2 is being caused by 2 H's, and signal C is also being caused by 2 H's. All right, that equals 7 H's, which does match up pretty well here to the formula. Let's go ahead and see if we got it right. And so we see here, this is our structure. We do have 2 carbons that each have 2 hydrogens, so that looks good. And then we also have another one that has 3, a methyl group. So this looks like a pretty good analysis. All right. So that's really all there is to it. It can be a little bit more difficult sometimes, especially if you don't have integration units and the lines bleed into each other. But what you have to do is you have to get adept at sort of distinguishing where you have these little funny bumps and figuring out where one ends and one begins. That being said, you will definitely more often than not be given integration units of some form. That helps a lot. All right, so until next time, I'm going to sign off now. The next video will be on spin-spin splitting, which is our final factor that we have to take into account, and then we will start analyzing problems, putting everything together.